Hey, how's it going, guys? This is part 3 of my Gregtech 6 Fission Reactor tutorial series. Last time, we talked about the critical reactors and how to build those, and we also talked about breeder reactors and how to build them, and also how to automatically control some aspects of your reactors so that you don't have to enable and disable them yourself. In this episode, we're going to be going over some more advanced reactors. Namely, I'm going to talk about the molten thorium cooled reactors. I'm going to talk about how to improve some of your reactor designs to make them a little more efficient and how to automatically control some of them a little bit more. And I'm also going to be talking about different kinds of reactors like moderated reactors and burner reactors. So before we get started building a molten thorium salt reactor, I want to go over a couple of different things. The first thing to go over is what is molten thorium salt? If we look at the recipe for molten thorium salt, you'll see it's a combination of 1 thorium dust with 20,000 liters of molten lithium chloride, and you get about 20,000 liters of molten thorium salt. So what makes this different from other coolants? Well, molten thorium salt doesn't work like other coolants in the reactor. So if you remember how the first kind of reactors we built worked, they used distilled water and they generated steam, and then we used that steam to spin a turbine. And with the other kinds of coolants, like in our breeder reactor, with sodium, you get hot sodium, or with other coolants, you'll just get their hot coolant, and then you use heat exchangers to extract the energy out of that coolant. Molten thorium salt doesn't work like either of those kinds of coolants. Instead, when you use molten thorium salt to cool down your reactor, you'll instead get molten lithium chloride, which you remember is one of the ingredients in molten thorium salt. So what is the point of this? Because you might have remembered there are fuel rods that you can make out of thorium, and there's also breeder rods that you can make out of thorium. So why would you want to use it for this molten thorium salt as a coolant that isn't actually able to generate power itself? To answer that question, we now need to go over the stats. And the first stat that might stand out to you is the heat capacity of molten thorium salt. If you look, the heat capacity is 2,560,000 heat units per liter of molten thorium salt. So that on its own is quite significant. But if you remember, for 1 thorium dust, we actually get 20,736 liters of molten thorium salt. So the math on that is 53,084,160,000 heat units per unit of thorium that you use. So that's pretty significant. Even though you don't actually get to generate any power with that, you can cool down your reactor pretty significantly with this and for a long time. So that 1 thorium dust that you might use to generate that salt is going to go a long way in your reactor. So don't worry too much about consuming this at a very fast pace. It's not going to be used nearly as quickly as you might have thought. Now, the other stats we need to take a look at are the self stat, the emission stat, and the amplifier maximum stat, as well as the offset for the factor divisor. And we'll start with the self stat because you might have seen this is 0. So essentially, if you use this molten thorium salt in your reactor, your fuel rods will not actually emit any neutrons onto themselves. Likewise, the emission is 0.5. So that means whatever fuel rod you use is actually going to emit half as many neutrons to its neighbors. And so you might be thinking, well, this is a lot of downsides. First of all, we're not actually able to extract any power from this molten thorium salt, and we're not getting any of the self neutrons, and we're not getting any of the emission neutrons, or rather, we're getting half as many emission neutrons. And those are pretty big downsides, for sure. But if you look over here, the amplifier for the maximum is actually 4. So that means whatever fuel rod you put inside of the reactor, inside of that molten thorium salt, has its maximum multiplied by 4. So if we go again and take a look at uranium-235, for example, the maximum is 2048. So if you use this with molten thorium salt, it would become 8096. So that's pretty significant. That means you would be able to have up to 8096 neutrons on a uranium-235 fuel rod and still not deplete it any faster. That's pretty significant. And now finally, the other most important stat is the offset for the factor divisor. So just like with sodium and tin, this will actually make it so that you can achieve criticality with 1 less neutron source than with any other coolant. So that means that for uranium-235, for example, you only need 3 adjacent neutron sources. So you can see there are some pretty significant downsides with molten thorium salt, but there's also some upsides. So now that we've gone over molten thorium salt and some of its unique characteristics, I just want to go over a couple of more advanced reactor control topics. Now, the first one that I want to talk about is the concept of controlling individual reactor rods. Up until this point, with the redstone machine switches we've been using, the concept of turning the reactor on or off has been a completely wholesale on or off of all of the rods inside of the reactor. Now, if you're doing a more advanced build, like we're going to be doing with the thorium salt reactor, you're going to want to be able to control individual rods inside of the reactor. Now, how do we do that? Well, first of all, you're going to need to have your rods enabled by some kind of mechanism, ideally with redstone, not with a soft hammer. You're going to have them all turned on, and then you're going to use something called a redstone selector cover. Now, if you haven't used these before, essentially what they do is they allow you to select certain properties of whatever machine they're placed on using redstone. And for the nuclear reactor core, that's actually going to be controlling rods with redstone. And you're going to be able to control individual rods inside of the reactor depending on which redstone signal you apply to the side of the reactor with that selector cover. Now, the way this works in a little more fine detail is that this is a binary system. So if you are familiar with binary, this will make a little more sense to you. So the orientation of this is north, and it's going to go top left, top right, bottom right. So you can think of this as 1, 2, 4, and 8 if you're familiar with binary. So the number 1 redstone power is going to control that top left reactor rod. The number 2 is going to control that bottom left one, and so on and so forth. So it's going to count from here, and it's going to go here, and it's going to count through binary. Now, you don't really need to understand binary to be able to use this system. You can just set up something like I've set up here and kind of just see which reactor rod this controls before you actually set up your full reactor. And just as a note, you can use any kind of reactor rod that's not a fuel rod if you want to be able to test like this. So you can put reflector rods like I did, or you can even put empty reactor rods, and that'll sort of help you demonstrate to yourself how you're going to actually be able to control this. So this will actually allow us to control individual rods or multiple rods if we wanted to inside of the reactor using redstone. Now, another concept I want to talk on is this concept of the universal extender and how it works with the nuclear reactor cores. Now, if you're not familiar with universal extenders, essentially what they do is they expand out whatever side of the machine you put them on into another full block. So what that's going to mean is that we can expand the side of this nuclear reactor to an additional block, and then we get all of those additional sides to work with. And that's going to be really useful for some of your more advanced reactor buildings. So we're going to expand our system a little bit here, and we're going to do the same thing with the selector cover. So let's put one on the side, and we'll put it on the universal extender this time, and you'll see that it works exactly the same way. So what this really allows you to do is make much more complicated builds because you're able to expand the entire reactor by a block. And now this will work for Geiger counters, it'll work for fluidometers, it'll work for fluid pumping, and pretty much anything you can do to the reactor core itself. So this is really useful. And we're going to actually use it to input fluids and control the reactor and get the Geiger counter reading off of it when we build our molten thorium salt reactor. So this is going to be your best friend when you build reactors, and I highly suggest you build a couple of them if you're planning on building anything more advanced. Now that we've gone over the universal extenders and redstone selector covers, we can get started on building our molten thorium salt reactor. This is going to be another example of a breeder reactor, but it's going to have a couple of key differences compared to our previous breeder reactor. So you'll see here that I'm disabling the cold coolant sharing faces on these two reactor cores here, but I'm going to have this reactor core share its coolant with the reactor core back here. Now, there's going to be two reasons for this. The first is that we're actually going to use different coolants in our reactor cores. So these two cores here are going to have distilled water, and this core is going to have molten thorium salt. Now, why are we doing this? Well, if you remember last episode, the reactors that we built before had the same coolant in all of the chambers of the reactor. So they all had the exact same coolant and they were sharing it amongst themselves. But you don't actually have to do this. You can mix and match coolants in different cores of the reactor and it'll work just fine, provided you understand how that coolant impacts the performance of your reactor. Now for breeder reactors specifically, it is actually better to use a coolant like water in the reactor cores that only have your breeder rods in them, such as this one. And the reason for that is because breeder rods aren't impacted in any way by the coolant that they're submerged in other than the heat generation stat of that coolant. So the stat that determines how many heat units per neutron is the only stat that affects the breeder rod. So for this example of sodium, the sodium gets 1/6 of a heat unit per neutron. And if you want to maximize the efficiency of your reactor for power, you're actually going to want to not use sodium or tin or molten thorium salt in the reactor cores that have your breeder rods. Instead, it would be better to just use distilled water. That way, you get the benefit of that one-to-one exchange for heat units and neutrons, and you can also directly generate steam and turn a turbine with it. So we would be better off just using distilled water for our breeder reactors that have the breeder rods in one reactor core. And that's what we're going to do over here. And in this reactor, we're actually going to have 2 breeder rods in there, and I'll explain why in a moment. But first, let's fill these guys up with water, and we'll let that guy fill, and we'll have him fill like that. And then we'll get a fluidometer just so we can monitor the water levels, and turn this guy to percentage mode. Whoops. Just like we do usually. And then we will capture the steam that comes out and also set up a turbine like this guy. And we will finally connect him like that. So that's going to be our steam loop for the breeder reactor cores. Now, once again, you'll notice that we have 2 reactor cores filled with distilled water, and we're going to use 2 breeder rods. Now, why are we doing that, and how is that possible? Well, instead of using uranium-235 in this reactor, we're actually going to move to a different fuel, and that's going to be plutonium-239. Now, if you remember from last episode, the breeder reactor we built was actually breeding uranium-238 into plutonium-239. So once you actually finish the breeding of your breeder rod, it'll turn into a plutonium-239 enriched rod, and then you can centrifuge that and you'll get some plutonium-239, which you can use to turn into the fuel rods. Now, a plutonium-239 fuel rod is more than 4 times as powerful as a uranium-238, or rather a uranium-235 fuel rod. And you'll notice specifically for the self and emission stats, those stats on the plutonium rod are actually 4 times higher. The maximum and duration stats are 2 times higher for plutonium. So the maximum is 4096 neutrons as opposed to 2048, and the duration is 20,000 minutes instead of 10,000. And you can see that converts to about 333 hours of real life time on the plutonium rod. So it lasts a really long time. But the factor stat on the plutonium is really the most important change between uranium and plutonium. So the factor of uranium-235 is 1/4, but for plutonium, it's 1/3. And if you remember, factor is how many adjacent neutron sources you need to go critical. So this is a big benefit. It means that plutonium, by default, is actually the same as uranium-235 while using a coolant that makes it so that the factor goes down by 1. So plutonium by default doesn't actually need that kind of coolant like sodium or thorium or molten tin. You can use any other kind of coolant if you want to go critical, and you don't need to use those special coolants. Now, we are going to use one of those coolants, obviously. We're going to use molten thorium salt, and because of that, we're actually going to get a factor of 1/2, which means we only need 2 adjacent neutron sources. So that's why we're going to use 2 breeder rods, because we have 2 free faces on our plutonium rod if we use reflectors. Now, the other stats that you're seeing here are the stats that are modified by the molten thorium salt. So the self stat is going to get set to 0, the emission stat is going to get set to 64, and the maximum stat is going to get set to 16,384. And that's a really, really high maximum stat. If you remember our breeder reactor over there, we never saw a neutron level that high. The breeding level that we're at is probably close to 11,000 or 12,000. So because plutonium is going to sit in the same power band, because we know how many neutrons we need to actually breed that breeder rod, we're going to set it to pretty much the same power level. So we're always going to be below the maximum stat of our plutonium rod. So that means we're going to get the full lifespan of our rod as opposed to uranium. And even if we were to use uranium with molten thorium salt and we were to get that increased maximum, we would only get 8192 as its maximum, so we would still be above the maximum of uranium-235 even if we used molten thorium salt. So we would still be draining that rod faster than normal. But with plutonium, we actually will always be below the maximum because of how it raises it. So that's really how that molten thorium salt benefits us, and that's why it's so efficient. Even though you're consuming thorium with it, you're only consuming a little bit, and the benefits that you get for your actual powerful fuels like plutonium are going to be huge. You're going to get a lot of savings on these guys. So let's continue building our reactor, and we're going to use plutonium as our fuel. Whoops. So we'll put them there, and then we will put some breeder rods in these reactors here. And we will put some reflector rods in these guys here. Now we're going to use our universal extenders on this reactor core here, and we're going to set the primary face here and the second face in there as well, because we don't need that secondary facing. And just as a note, you always have to set the primary facing of the universal extender towards the machine that you actually want it to interact with. So because of that, we're going to put a drum on top of it. Oops, there we go. So let's put the drum there, and we'll let it fill. And we will put molten thorium salt onto this guy. And you can see he's filling. So he's going through the universal extender and filling that core. And we're going to put some Geiger counters on this guy. Where are my Geiger counters? Yep, right there. So we'll put one there, and one there. We'll put a Geiger counter on that guy. And just as a note, the neutron reading on this breeder rod is going to be identical to this one because they're interacting the exact same way with that plutonium rod. So you only ever need to get the readings off of one of the breeder rods as long as they're the same one and you put them in at the same time. So you don't ever need to monitor both of them unless you care specifically about the way that they're, I don't know, being automated. But for this demonstration, we're just going to read it off of one. So we're going to have our Geiger counters there. We're going to have a drum down here, and we're going to collect the molten lithium chloride that the molten thorium salt gets turned into. So we're going to fill that guy. We'll put some fluidometers as usual, just to monitor all the levels here. Set these guys to percentage mode. We'll put some more thorium salt in here. There we go. And you'll see just how little molten thorium salt is actually used in this reactor, even though we're going to be using very high neutron levels. Now, finally, what we're going to do is we're going to set a redstone selector onto this universal extender, sort of similar to how we did it over there. Now, what we want to happen, because we only have 2 reflector rods, is we're going to toggle one of these rods on and off in the same core as the plutonium rod. And if you remember, the selector cover allows us to individually toggle rods inside of the reactor. So the reason why we're doing this is because we have the breeder rods in their own reactor cores, as opposed to the way we did it before, where one of the reflector rods had its own reactor core. Now, the reason why I'm doing this is because breeder rods need to be measured independently of the fuel rod, and you really, really want to do it this way every single time you do breeding. You don't want those rods to be in the same core, because when you get your reading with the neutrons, it's going to take a sum of all of the all of the neutrons in the reactor, as if it was the same kind of neutron level. So it reads the entire reactor core and gives you that sum. And that's not useful for us. We need to be able to see how many neutrons are on the fuel rod and also how many neutrons are on the breeder rods. We don't want that to be added together. We want to be able to monitor and control those levels ourselves independently. So you always want to put the breeder rods in their own reactor cores and the fuel rods in their own cores as well. It would be okay if we had the fuel rods all together in the same core, but the breeder rods you definitely want to have in their own cores. So that's why we have to use the selector cover here, because we need to disable and enable the reflector rods that are in the same core as the fuel rod, and we don't want to touch any of the other rods, so we can't turn them all on and off at the same time. So what we're going to do is we're just going to set up a little system to keep this guy turned on. So let's set a redstone machine switch. And actually, before we do that, it's good to note that you should always check how your configuration is going to be set up here by doing the same setup that I had there. So you want to put some rods in here that are not fuel rods, and then test out what the selector cover is going to be controlling. So what we want to happen is either for this bottom left rod to turn on and off, or for the top right to turn on and off, and everything else should be enabled at the same time in that core. So let's build a little redstone circuit here. just so we can test how we can do this. And I was hoping that I could use blue schist. Let me go and grab that here. Oops. All right, and then we'll put this here like that. And we're going to want to get that neutron count from this sensor. So what we're going to do is we're going to set this to hex mode, and we're going to set a less than. There we go. So as long as we are less than, let's say, definitely going to need to be 20F0 maybe. Let's see. All right, whoops, that's a little too high. Let's do 2F00. I think that should be fine. So we're going to use that, and we're going to pull off a red alloy wire, and we're also going to put a red alloy wire here. And then we're going to use the red alloy wire to control redstone. So we'll do like this. Actually, like that. That way it doesn't connect in any weird way. Like that. Okay. So we can see here. Oh, wait, why is it not connecting? Oh, it's because I didn't connect that guy there. There we go. So you can see this redstone signal, which is going to be 10, or actually it's 8, I guess. Or is it A, the letter A? I think it's the letter A. So it's turning off those two rods there. So that means we still need to modify our circuit a little bit. So let's go back one more. So that's not good. That's going to turn off of our fuel rod. So we'll go back another one. That's still not good because that turns off both of our reflector rods. So we'll go back another one. And that one is okay. That leaves all of our rods on except for the reflector rod back here. And obviously this one isn't actually going to be used. So we can remove this and remove that. And this is good. This means we can use this exactly the way it is. So we'll keep that guy like that. And we will enable the 2 breeder rod cores. And I think we should be good to set this guy up. I don't think I'm missing anything. So let's go ahead and put our plutonium rod in. Actually, I think I need to set this above because, hold on, let's see. Yeah, we need to go to greater than that number. That way, every single rod is enabled all the time, except if we go above the value that we set. So let's put our plutonium rod in. That turns off. And what I actually want to do as well, to just add a little bit more control to our reactors, and as a best practice kind of thing, is to set red alloy wire onto all of these cores. That way we can independently control all of them with a lever. And that way we can turn off the breeder rods if we want to, or we can turn off the main reactor core just as a emergency kind of stop. And you're definitely going to want to do this in yours just in case you need to, stop your reactor for any kind of reason. So let's do blue schist and a lever on all of these guys. Oops. And we'll put levers. And then you can see we'll be able to control each one independently like this. So let's turn on the breeder reactor cores. And we'll turn on the fuel core. And we should see an accumulation of neutrons here. So we're going to let that guy build up. And we're going to set this Geiger counter on the left here to hexadecimal mode. Whoops, I didn't mean to do that. That way we can kind of see what the hex value is of the total of the neutrons in here. So if we need to tune that a little bit, we can always just use this reading to configure that Geiger counter. But we can start to see, we'll accumulate neutrons as we start to get above 10,000. So we'll just let that guy build up. Actually, I want to fill more distilled water into this guy. I think I forgot to fill him back up. There we go. And you'll see soon this is starting to heat up and spin its turbine. And now we're getting neutrons. And it actually didn't even take that many neutrons. It was, oh, something happened here. I think the breeder, why did that happen? Oh, you know what? It's because I forgot to put a steam outlet pipe here, which is completely on me. I forgot to hook that up. So we lost one of our breeder reactor rods. So let's put that back in. There we go. And now that'll be just fine. So don't forget to put a hot coolant output pipe. That's just a dumb mistake I did. But you can see we actually started breeding at a much lower power level. And that's because the emission stat is a little bit higher on plutonium, even though it's being reduced by a little bit by the thorium. It's actually being cut in half. It's still higher than it usually is. And the scaling that's happening inside of the, oh, oops, let me turn that down. That's a way too high power level, and I hate hearing that noise. Let's do it to like that. I think that should be fine. But you can see that the breeding is happening at a much lower power level in this reactor configuration because of the molten thorium salt, because the self stat is not being applied to the neutron scaling, and because the emission stat is being modified a little bit. We're actually only getting benefits from our emission, really. So we're actually able to start breeding at a lower power level. I think I set this a little too low. Let's set that to 2900, I think. I don't know exactly what that corresponds to, but it should be close enough. But you can see this is how you use molten thorium salt. And we haven't even gotten 1% of this tank filled up with the molten lithium chloride. So if we get a scanner and you look at this, we've only actually used 7 liters of our molten thorium salt. And we're actually going to be able to generate quite a bit of power from this. So if we hook up a adamantium axle here and a dynamo, I don't know, let's hook up an MV dynamo. I think this might be more even than it looks. And let me get a tachometer. We'll put that on there. Oh man, I hate hearing that noise. I just need to like turn that off a little bit. There we go. Jeez, I think it's still too high for this. Let's put a HV dynamo on there, or an EV. Nah, HV is fine. Dynamo, if I can spell. So let's get a HV dynamo and put them there. And you can see we're getting quite a lot of rotation units out of this little configuration. So even though the neutron levels we're working with are not, jeez, I guess EV is the right scaling here. There we go. So even though our neutron levels aren't actually super high, we're actually generating quite a bit of power here. So a molten thorium salt reactor, as you can see, is fairly efficient. It's much more efficient than the other configurations we use, and it doesn't use that molten thorium salt in any kind of large capacity. We still only used 11, and we've managed to generate quite a bit of neutrons. If we looked at the contributions to our breeder rod here, you can see we've already contributed, I think, where's the actual first one? So 256 million. We've contributed 6 million neutrons already, and we've only had this running for like 2 minutes. So you can see how efficient that is, both for breeding and for power generation. So this is sort of the high-end reactor type that you can build. But if you actually look at the construction, we haven't really put in too much more than we did with the breeder reactor or the critical reactor. The infrastructure costs are largely the same. And actually, you save a little bit of infrastructure costs compared to the breeder reactor specifically, because you don't need those heat exchanger loops. So this saves you a significant amount of infrastructure, and you don't need to worry about anything like a boiler. You just run straight steam through the entire system. So yeah, that's how you build a molten thorium salt reactor and use it to breed plutonium-239 so you can fuel it. So before we move on from breeder reactors for a little while, I just want to cover a couple of final notes about how the loss stat works on the breeder rods, as well as how you can detect when your breeder rods are actually done breeding. So for the loss stat, you might have been thinking when we were building our breeder reactors that it would have been better to have multiple low-level neutron sources rather than singular high-level neutron sources. Now this is not actually the case. You're going to want to use the high-level neutron sources. And the reason for that is because the loss stat of the breeder rods is actually subtracted from all incoming neutron sources individually. It does not subtract it from the sum of the neutrons that are coming in. So if we were to surround this breeder rod with multiple plutonium rods that were all emitting 1,000 neutrons, none of them would actually be contributing to the breeding because, again, the loss is subtracted from each instance individually. So you always have to exceed that loss stat on each side if you want to contribute. So what we can do instead is actually copy the reactor core that's here and put it on this side as well, and then we would have 2 instances of high-level neutrons, both exceeding that loss stat, and that would actually contribute twice as much to the breeding because we have 2 sources. So just keep in mind, the loss stat is subtracted from each source of neutrons, not the sum total of neutrons coming into the breeder rod. Now, moving on to how you can detect when your breeder rods are actually done. What you're going to want to do is monitor the highest level of a neutron that you're going to see on your breeder rods. So we're going to just take a minute and look at this neutron level here, and we're going to see when this actually maxes out and then resets back down. So it looks like 2600, a little over 2600 is how many neutrons are going to be on the rod before it resets. So when the breeder rod is actually done, the loss stat is no longer going to be applied to the incoming neutrons. So what that means is that The highest level that you see when the breeder rod is still a normal breeder rod is going to be exceeded when it turns into its enriched rod, which means it's done. So whenever we exceed our maximum, we're going to know that the breeder rod is done. So hypothetically, what we could do is monitor with a Geiger counter this reactor, and we could say when we exceed, and we'll say 2,700 because our maximum was 2,600. So we know if this reactor core ever goes above 2,700 neutrons, that this rod is done. So we could have some kind of system to disable this reactor core whenever it exceeds that neutron level. So once again, whenever your breeder rod is actually turned into its final product, which means it's done breeding, the loss stat is no longer applied, so it'll start to exceed the highest level of neutrons that you observed when it was still a breeder rod. So keep that in mind when you're starting to design your automation for your reactors. So up until this point, we've been discussing breeder reactors as the method that you use to move through the tiers of nuclear materials, but it's not actually the only way that you can do so. The other way to do it is through the depletion of your fuel rods and then the subsequent centrifuging of them in order to get their byproducts. So if we look in NEI at uranium-235, which is our base fuel, you can see that you get a couple of byproducts from it. So you get some zirconium, which you'll just use to create a new fuel rod. You get a little bit of uranium, and you get a little bit of plutonium dust. Now that plutonium dust is actually plutonium-244, which is different than the plutonium-239 we created in the breeder reactor. Plutonium-244 as a fuel is only half as good as plutonium-239. You can see all of its stats across the board are half as good, except for that factor. That factor is just one tier below plutonium-239, which puts it in the same tier of factor as uranium-235. Now, there's a couple of notes I want to make about this method of moving through the tiers of nuclear materials compared to breeder reactors. The first problem with doing it this way is that if you decide to dedicate your setups to burning your fuel rods rather than breeding, you're going to waste a lot of power and you're going to waste a lot of the potential of your fuel rods. So burner reactors are reactors which try to deplete the lifespan of their fuel rods as quickly as they possibly can. And obviously, that's the antithesis of what we've been discussing up until this point. Ideally, you want to maximize the amount of power you get per fuel rod so that you're not wasting any of the potential energy. But burner reactors are doing the opposite. They're burning their reactor rods as quickly as possible so that you can just get the byproducts. Now, it might seem like this is okay because you're going to get better tiers of nuclear materials, but if you look in NEI, for example, at plutonium-244, which is a tier above uranium-235 with this method, if you centrifuge that depleted rod, you only get a little bit of plutonium-241. Now, you might notice that this is the same trend that we saw with the uranium-235, which only gives you a little bit of plutonium-244. So as you keep moving up tiers, it becomes harder and harder to move to the next tier because you end up needing more fuel rods of that very base material, which is uranium-235. So this becomes very quickly inefficient in terms of how much uranium you use. You're going to end up depleting several hundred uranium rods before you end up at the last tier, which is Nequadria. Now, I'll go over Nequadria in a little bit, but I just want to note that there are 5 tiers in between uranium-235 and Nequadria, and with this method, you have to go through all of them, and they all become exponentially harder through this method. With breeding, you only have to actually pass through 1 tier of breeding and 1 tier of depletion to get to Nequadria. So if you wanted to, you could use uranium-235 to breed a material called naquita, which you get from the end, and you'll breed that into enriched naquita, which is a material that's very similar to plutonium-239, and then you can deplete this rod in order to get Nequadria. So you only have to do 1 breeding tier and 1 depletion tier with the breeding path compared to the depletion path, which you have to go through all 5 tiers, and you have to do exponentially more centrifuging and more depletion than you do with the actual breeding path. Now, another thing to note is that with breeding, you are still going to be depleting fuel rods. It's just going to be at a low rate. So eventually you'll still get some of those subtly higher tiers of materials, but I honestly wouldn't care too much about that. It's not worth going this depletion path, and I'm only covering it to make sure that you understand that there are different pathways in order to do this. But yeah, we're going to start to cover burner reactors, which are reactors that are designed to quickly deplete their fuel rods. So before we start building our burner reactor, I just want to quickly go over tritiated water, which is the coolant that we're going to use in that reactor. Now you don't have to care too much about any of the other stats, and what we're going to focus on is amplifier maximum and this moderate stat. So this amplifier maximum is a very small number that's less than 1, which means that our maximum stat on whatever fuel that we're going to use is going to be set to a very, very small number. And if you remember, if you exceed the maximum stat, the more you go over, the faster your fuel rod depletes. That's really good if we want to actually deplete our fuel rods at any kind of respectable pace. And tritiated water actually has the lowest multiplier for the maximum stats. In addition to that, tritiated water also has the moderates stat on it. So because of this moderate stat, if you remember from the first episode, we're going to be depleting our fuel rod from the start at a 4 times increased rate. So combined with the amplifier maximum being less than 1, we're going to be depleting our fuel rods at a very rapid rate. And you'll actually be able to see how quickly they'll deplete. And so we'll get started on building this reactor because it's not going to take very much. So we'll put some reflector rods around this guy because the critical reactor is the fastest way to deplete these. And we'll put some more reflectors here so we can just completely increase this guy over time. We'll have a drum filled with coolant. And we'll put a pipe to fill that guy. So we'll do this. And we'll have to make sure we set the hot coolant output on the bottom. And the coolant sharing face can be disabled. And once again, these reflector rods don't need to be in any kind of coolant because they are, they're not going to accumulate any neutrons, so it's not a big deal. We'll just make sure to disable all of the coolant sharing faces on them. Then we'll retrieve that hot coolant. We will put it into heat exchangers, and we'll just kind of start a line here if we need to. Actually, it would probably be better just put it here. So we'll do it like that, and then we will recycle our coolant. So you'll never lose any of this tritiated water because it is a normal coolant that does not, turn into like steam or anything. So you'll get a 1-to-1 conversion of the tritiated water into hot tritiated water. So don't worry about losing any of it. And actually what we're going to do is instead of doing this, we're actually going to use a universal extender just so we can get our readings a little bit easier. So we'll point the primary face there and the secondary face there. We'll put our drum there. And then we will connect this guy there. And that way we can get our Geiger counter readings on here. And we'll have to put the tritiated water into this drum, fill that guy up. So we should be able to see, yep, there's tritiated water in there. And this guy has his hot coolant output face towards the bottom. And we'll just make sure to top this off. We'll put a fluidometer so we can just monitor this. And you'll see it'll never go below any kind of value that matters. And we can enable these guys here. And then we'll have a little control mechanism right here to enable and disable the reflector rods. So let's put a redstone. Actually, we have one in our inventory here. We'll put a redstone machine switch onto this reactor and put a redstone signal here. So we'll say as long as we are below, I don't know, we'll put it at, let's say 2,000 neutrons. It's not going to take very much to exceed the maximum of this uranium rod, so it's not going to be going too high. But we can start to set that guy to run. And I'll just use my sensor to make sure there's no backup of any of the tritiated water. It doesn't look like there is. And you can see we're accumulating neutrons. We're going critical. Oh, actually, you know what? We're going to need to connect that guy so that we can fully go critical. So we're going to start to get more and more hot tritiated water. And we should probably just put another heat exchanger just for safety reasons, because I don't know exactly how much coolant is going to be circulating. Shouldn't be too much, but you never know. There we go. I think that's more than enough to handle the throughput. So you'll see this guy will start to be controlled the standard way that we controlled our critical reactor. But if you look, if we grab our fuel rod here, you could see the lifespan has already gone down by almost 130 minutes. And that's only been in there for, I don't know, less than a minute. So this is the fastest way that you can deplete your fuel rods in order to move up to the next tier. And we can actually raise this quite a bit higher if we wanted to. And you'll see there's an exponential increase in the depletion of that rod. So let's let this guy go to 5,000 neutrons, and I'll just put a couple more heat exchangers because it's going to get pretty hot So let's hook these guys up real quick. And we'll hook them up over here. So like that. There we go. So all these guys will run, and I think that should be more than enough to handle the throughput. Yeah, I don't think that's going to be a problem. So let that guy run for a minute, and then if we take him out again, you'll get to see that it has been depleted significantly when we take it out. Let me just get rid of some of these other ones. So this guy's going to keep cycling its neutrons as it goes up and down. And then we can take this guy now, and you'll see it's already gone down almost 500 minutes, and it's only been in there for like 2 minutes. So if you let this sit for a little while and you keep letting it go to higher neutron levels, it'll deplete faster and faster. That's going to be the same with the higher tiers. But another problem with this burner reactor design is that with these higher tiers of nuclear materials, their maximum and their duration starts to get higher. So you end up with this problem of not only needing a lot of this base tier of material, but also the subsequent tiers require more and more time to deplete. So even though you might be, trying to do this as efficiently as possible and exceeding the neutron levels, you're going to need to have more and more infrastructure in order to burn out those fuel rods, as opposed to a breeder reactor, which is kind of like a set and forget, stable design. You know exactly how much time it's going to take. And the entire point is to get to, next tiers of fuel while you're also generating power. So again, I really want to emphasize just how bad this reactor design is, both in terms of power and also getting to the next tiers of material. There's no real benefit to doing this way unless you just care about the realism of moving through the different tiers of material. But I personally don't think it's worth the trade-offs. This is just extremely inefficient. So this is a burner reactor design. You can see it's pretty stable. It's not overly complicated. But again, this is just a very inefficient way of using your fuel rods. And I think it's personally a big waste of time. So I'm going to bring this episode to a close here. Just as a recap, we went over molten thorium salt and how you can use it in your reactors. We covered more advanced reactor control mechanisms and how you can implement them. And we covered burner reactors as an alternative to breeders to move through the tiers of nuclear materials. In the next episode, we're going to focus on the most advanced reactor designs, which are going to be reactors that are fully self-contained with the ability to generate their own water in order to fuel their turbines. And we're going to have a system to automatically replace fuel rods and the breeder rods so that you don't have to actually worry about any of those systems anymore. We're also going to focus on the highest tier of nuclear materials and how you can implement them in your reactor. So we're going to talk about Nequadria and how you can breed into that. But for now, I'm going to bring this episode to a close, and I'll see you guys next time.